Hey guys, so we're in section 6.6, exponential and logarithmic equations. And so this section is basically one of the culminations of using all the techniques that you've learned thus far in algebra. Um, so we're not going to cover every single type of problem that you'll see in this section and that might possibly show up on the final. But you should you should definitely go through all the recommended problems, and make sure that you can solve all these different types of questions. But they basically boil down into um, four techniques for solving these types of equations. And so the first set we're going to look at is solving exponential equations. And the technique is finding common bases. So here we have our equation. And remember that anytime we're solving an equation, we're trying to get a variable by itself. And so there will be two techniques for solving exponential equations, and likewise there will be two techniques for solving logarithmic equations. Because we're solving equations, our goal is to just get x by itself. All right, so this first technique, we're going to call it common bases, and it relies on the fact that x to the a is equal to x to the b if and only if a is equal to b. So, as an example, if we have 2 to some power is equal to some other power, well, this is only going to ever be true if x and y are the same value, because remember that exponential functions are 1 to 1. So if their y values match, that means their x values must match as well, right? Okay, so the goal here is basically to get both of the sides to have the same base for the exponent, and then set the exponent arguments to each other and solve that as a linear equation. So here we have 2 to the 5x is equal to the square root of 2. And so it's going to take a little bit of ingenuity on our part here to be able to write both of these sides so that they have the same base. And this is going to really come down to how comfortable you are with your algebraic techniques that we've used up to this point in the semester. And so, well, since we have the square root of 2, remember that radicals, square roots, cube roots, whatever, they can be written as exponents, right? And what kind of exponents? Well, rational exponents. So there's a fraction that we can write this as to keep the base as 2. And it is 2 to the 1/2 power. Recall that the square root of 2 is the same as 2 to the 1/2 power. Now, luckily, the left-hand side is already written as a power of 2. And so now we can employ this, this logic here, because exponential functions are 1 to 1. That means 2 to the 5x power is equal to 2 to the 1/2 power only when the arguments for the exponents are equal. So what we can do here is kind of just ignore the exponents and set the arguments equal to each other. And so we set 5x equal to 1/2, and now we just have to solve for x. Well, we want to get rid of the 5, right? So what do? Well, we multiply the left side by 1/5. We multiply the right side by 1/5. And we get this just gives us x, because the 5 on top and the 5 on bottom cancel. And we get x is equal to 1/10. So now you'll notice we can check this. We can plug this back in. 2 to the 5 to the 1/10 power is equal to square root of 2. Well, 5 times 1/10 is just 5/10. Well, that's 2 to the 1/2 power. And we know that 2 to the 1/2 power is the same as root 2. And so we check our work and we make sure that everything checks out. Sometimes when you do exponential and logarithmic equations, you're going to come up with values that don't make sense. So you always want to check your answers just to make sure that they are valid. They're not extraneous, which means they're just not solutions that you get from doing algebra, but don't actually make sense in the context of exponents or logs. Okay, so technique number 2 for solving exponential equations is using logarithms. And so if you try to apply the same technique number 1 here, you're going to realize that there's no way to write 3 as a power of 2, because 2 to any power is not 3, right? These are relatively prime numbers. And so, well, we know ultimately our goal is to get x by itself. However, most of the algebraic tools that we have right now are only really useful when x isn't hanging up as the argument of the exponent, right? We want it down on the ground, kind of where the 2 is. And in the last section, we saw that we have rules for logarithms: the product rule, the quotient rule, and the power rule. And one of those rules allows us to bring the exponent down to ground level, essentially. And so that will be the power rule of logarithms. So that's what we're going to employ here. So what are we going to do? Well, we're going to take the natural log of both sides. And so we're going to take the natural log of the left side. It's going to be the argument of the natural log. If we do it to the left side, we have to do it to the right side. Okay? Now, we have the power rule of logarithms, which says that if the argument is raised to a power, we can put it out in front as multiplication. And so we have x times the natural log of 2. And not only can we do that for the left side, but 3 has an exponent, so we can put that out in front too. So we have x plus 1 times the natural log of 3. Okay. And so, well, here we have a binomial being multiplied to the natural log. So what we can do is FOIL this, right? We can multiply that to the natural log and then multiply that to the natural log. And so, well, the left side stays the same. And the right side becomes x natural log of 3 plus 1 natural log of 3. And I'll write this way so it doesn't look like another L. Okay, and so from here you may be asking yourself, well, what am I supposed to do now? Well, recall that when we're solving equations, we always get like terms on the same side. So, well, this one has an x, and this term has an x, so why don't we go ahead and group them on the same side? And so what we'll get is x natural log of 2 minus x natural log of 3. Subtracting x natural log of 3 from both sides, so it's just going to leave us with 1 natural log of 3. And recall that we want to get x by itself, right? And so you may be asking, well, how are we going to do that? Well, like I said in the beginning of the section, this solving logarithmic and exponential equations is the culmination of all the things that we've learned in algebra. And so the next step from here is to factor x out, because this is x times natural log of 2 minus x times natural log of 3. The greatest common factor is x, so we can go ahead and factor that out. And it gives us natural log of 2 minus, right, and then natural log of 3. And we can see here that if we were to FOIL this, we would get right back where we started. And so, well, 1 times natural log of 3, I'm just going to write that as natural log of 3. And so we have x times this binomial, and since our goal, recall, was to get x by itself, what we can do here is just divide both sides by the binomial. Natural log of 2 minus natural log of 3. And do that on this side too. And we get x, right, because this becomes 1, is equal to the natural log of 3 over the natural log of 2 minus the natural log of 3. Okay? And so now we got x by itself, and there's our solution. All right, so now we looked at two techniques, one using logs and the other using common bases. So technically, the using logs technique is more powerful than the common basis technique, because the first technique only works if you can somehow write both sides of an equation as having the same base. But the using logs one, even if they could possibly be written as the same base, you can still use the second technique and solve it. Like solve the first problem using the second technique. However, sometimes it's just simpler and faster to use the common base technique. So if you see an easier problem where you think you can write them as the same base, go ahead and do that. It'll be faster. And for the problems that you feel like there's no way of using the common base technique, that's when you use the log technique. Okay? And so those are the two techniques for solving exponential equations. They're called exponential equations because the beginning, like the first, the way it started was an exponential equation, right? It didn't end up that way, but that's how it started. Okay, so solving logarithmic equations. We also have two techniques here, and the first technique is called condensing the log. And so we covered this in the last section. To condense logs, we use the three logarithmic properties. And so what we have is log base 2 of 2 plus log base 2 of 3x minus 5 is equal to 3. And so this technique, we're going to try to write the left-hand side as just one logarithm rather than having two logarithms added together. Well, to be able to do that, first we need to have the coefficients match, and lucky for us, they already do. Are the bases the same? Yes. Okay, and so we have the same base being added to another log of the same base. So which rule can we use here? Right, we have the product rule, the quotient rule, and the power rule. And remember that sums become products, so we can use the product rule to rewrite this as log base 2 of 2 times 3x minus 5. And the right hand side stays the same. And so we can do a little simplification here and write log base 2. We can FOIL this, right? 2 times 3x is 6x. 2 times negative 5 is negative 10. And now what we can do is we can rewrite this logarithm as an exponent, right? We have the changing from logs to exponents. We have log base b of argument a equal to y. This turns into exponent base b. Argument y is equal to a. So using this, we can rewrite this logarithm as 2 to the third power is equal to 6x minus 10. Okay. And well, we can simplify this. 2 to the third is equal to 8. 8 is equal to 6x minus 10. We'll add 10 to both sides here. We'll get 18 is equal to 6x. And we have 18 is equal to 6x. Divide both sides by 6, and we get x is equal to 3. Okay. And so let's plug that in quickly to check to see if it works. Well, 3 times 3 is 9, minus 5 is 4. Using the properties of logs, log base 2 of 2, log base 2 of 4, 2 times 4 is 8. And so we have log base 2 of 8. And that evaluates to 3. So let me just log base 2 of 2 plus log base 2 of 3, and we're going to plug in 3. Okay, and so here 3 times 3 is 9, minus 5 is 4, so we get log base 2 of 4 plus log base 2 of 2. Well, we can use our product rule for logs here because they have the same base. This becomes log base 2 of 8. And we know that this evaluates to, well, what is it? Well, we can call it y. 2 to the y is equal to 8. Well, what is y? What can y be? Well, y has to be 3, and so it checks out because 3 will be equal to 3. So that solution works. Cool. All right, and the second technique for logs is also the common base technique. So I'm going to create a line here so we don't get confused from what we wrote before. And so the common base technique basically works the same way as it does for exponents. which says log base b of x is equal to log base b of y if and only if x equals y. And this also works because logs are one-to-one functions, right? Logs and exponents are inverses, and inverses must be one-to-one, right? Okay, so we're going to use that same idea, and basically all this really boils down to in layman's terms is if you have two logs that equal to each other, you've condensed them into one log on each side. If the bases match, then the only way for them to be equal is if the arguments match. So luckily for us, on the right side, this has already been condensed into a single logarithm, but the left-hand side has not. Okay, so just give me one moment to see if I've written down these bases correctly. Okay, so I think I have written them down correctly. They should be log base 10, but I suppose it really doesn't make a difference anyway. Okay, so the idea here is that we want to condense both sides now. And luckily for us, like I said before, the right-hand side is already condensed into one log, but the left-hand side is not. So what do we need to do? Well, we need to condense this using the quotient rule for logarithms. And since we have a subtraction, that tells us we can change this into a single log using division. So we have 3x minus 2 with the 2 on bottom. And so the left-hand side is now just a single log. And so is the right-hand side. And since their bases match, right, they're both base 10. This is when we don't write base 10. And so if the bases are the same, that means the only way these two logs can evaluate to the same value is if the arguments are the same. So we just take what's inside the parentheses and set it equal to each other. And now we solve. And so we want to get x by itself, so let's just multiply 2 to both sides. That cancels the 2 on the left side. And then on the right side, we have to FOIL this 2, right, because we're working with a binomial. 2 times x is 2x, 2 times 4 is 8. And now we're just working with a regular linear equation, right? These should be our bread and butter at this point. And what do we want to do when we're working with a linear equation like this? Well, we want to get all the x's on one side and everything else on the other side. So we'll subtract 2x from the right side, subtract it from the left side. This gives us x minus 2 is equal to 8. We add 2 to both sides, okay? And so we get x is equal to 10. And now let's check to see if it works. Log base 3 times 10 minus 2 minus log base 2. Nope, not log base 2. Log base 10 argument 2 is equal to log base 10 plus 4. Well, 10 plus 4, that gives us log base 14. 3 times 10 is 30, minus 2 is 28, so we have log of 28 minus log of 2. Well, we use the division, the quotient rule for logarithms, so this tells us this is log of 28 over 2, and that's going to give us log 28 divided by 2 is 14, and so both of these sides are both log 14, so our solution checks out. Okay, and so there will be plenty of example problems, or excuse me, plenty of homework problems on this section, and I recommend that you go through as many of them until you recognize the techniques as possible, because just like with everything else, watching someone else do the algebra may make it seem like it's easier than it is, but I can tell you that plenty of people forget how to solve these exponential equations here. Even in calculus, these will come back. So they're really important to be familiar with using the techniques. So, well, that's it for this one. And if you have any questions, let me know. I'll see you in the next video.